What if I told you that building artificial volcanoes on Mars might be the key to transforming the Red planet into a second Earth? Although it sounds like science fiction, this groundbreaking approach to terraforming is not entirely out of reach. But now you might be asking, how exactly do we construct volcanoes on an alien world? And can they truly generate enough heat and atmosphere to make Mars habitable? Today, we'll delve into this revolutionary concept that could redefine our understanding of planetary engineering. Why volcanoes? The power and potential of volcanic activity. Throughout Earth's history, volcanic activity has been a crucial force in shaping climate and environment. Massive volcanic eruptions release vast amounts of greenhouse gases, like carbon dioxide and water vapor, into the atmosphere, leading to global warming. Additionally, these eruptions emit significant sulfur aerosols that can reflect sunlight in the stratosphere, causing short-term cooling effects. However, in the long run, the greenhouse effect is more significant. On Mars, we face a challenge. How do we inject greenhouse gases into its thin atmosphere on a large, continuous scale while releasing significant heat to kickstart a self-reinforcing warming cycle? Artificial volcanoes present an ideal solution to this problem. They are not just simple heaters but are planetary-scale climate regulators. How do artificial volcanoes work? Constructing artificial volcanoes doesn't mean just piling up a hill on Mars and igniting it. It's a highly complex engineering task that requires our most advanced scientific techniques. This process involves several key steps. First, we need to identify suitable geological sites on Mars. Ideal locations would offer relatively active geothermal activity, thinner crust, and resources rich in carbon dioxide and water ice. These areas could provide the energy source and fuel needed for artificial volcanoes. To trigger volcanic activity, we would need to drill deep below the Martian crust, perhaps reaching the mantle. Using high-energy nuclear reactors, we can provide additional energy to deep geothermal systems, melting the rock and ice beneath the surface. The immense heat generated by nuclear reactors would be the core driver of volcanic activity. Once sufficient nuclear-driven heat is produced, subterranean rock and ice melt, forming magma and high-pressure gases. Under pressure, these gases and magma would erupt through pre-constructed channels, simulating natural volcanic eruptions. Unlike Earth's volcanoes, these artificial versions would be precisely engineered to maximize atmospheric transformation. They would release large quantities of greenhouse gases, including carbon dioxide, methane, and water vapor, which would accumulate in Mars' atmosphere. In addition to releasing gases by melting rock and ice, we could utilize Mars' polar resources. The Martian poles contain substantial amounts of dry ice, solid carbon dioxide, and water ice. The heat from artificial volcanoes could warm these polar ice caps, releasing more carbon dioxide gas and accelerating the greenhouse effect. The positive feedback loop of artificial volcanoes. Phase 1: initiating the greenhouse effect. The carbon dioxide and water vapor released by volcanic eruptions would begin to thicken Mars' atmosphere, triggering an initial greenhouse effect. These gases effectively absorb solar radiation and prevent heat from escaping, gradually raising Mars' surface temperature. Phase 2: melting the ice caps. As temperatures rise, dry ice and some water ice at Mars' poles would start to sublimate or melt. This releases more carbon dioxide and water vapor, further enhancing the greenhouse effect and creating a positive feedback loop. More greenhouse gases lead to higher temperatures, and higher temperatures release even more gases. Phase 3: emergence of liquid water. when Martian atmospheric pressure and temperature reach certain levels. Liquid water can exist stably on the surface. The presence of water would be a milestone in terraforming Mars, as it is the foundation of life and can establish a water cycle, further regulating the climate. Phase for establishing an ecosystem. With liquid water and a thicker atmosphere, we can start introducing pioneer species like microbes and algae. These organisms can produce oxygen through photosynthesis, creating conditions for more complex ecosystems and human habitation. This phase might take thousands of years but represents the ultimate goal of terraforming Mars. Technological and logistical challenges. Technological challenges: do we have the drilling technology, nuclear energy capabilities, and engineering expertise to build and sustain such a massive project on a distant planet? Creating a giant climate machine that can operate for centuries will test the limits of human engineering. Resource challenges: building and operating artificial volcanoes requires massive amounts of energy and materials. How can we efficiently source these resources from Mars itself and avoid placing significant stress on Earth's resources and environment? Time challenges: even if everything goes smoothly, terraforming Mars might take hundreds or thousands of years. This endeavor requires unparalleled foresight and determination to initiate a project benefiting countless future generations. Despite the challenges, the dream of transforming Mars into a second Earth continues to inspire scientists and engineers to push the boundaries of exploration. The concept of artificial volcanoes offers us a tangible, feasible path forward. It's about creating a new home and a testament to human ingenuity, creativity, and resilience in the red sands of Mars. Perhaps one day, we'll see towering artificial volcanoes erupting not as symbols of destruction but as beacons of human hope, lighting our way to the stars and beyond.